of ISMM, and yep, we're going to have a great few papers here. My name's Steve Blackburn. I'm going to be the session chair, and without further ado, we're going to hear from Nadav Amit about enabling huge pages for real-world executables. So thank you.
So I hope we are all awake at this time of the day. Let's talk about huge pages and huge pages for code. Why should we care about it? Well, as you know, every instruction that we need to execute, the first thing, the CPU needs to read it, needs to fetch it. And for doing so, it needs to translate its virtual address into physical one. Now, this translation can, in the worst case, require 5 levels of indirection, so we need potentially to do 5 memory accesses. Obviously, this is too slow. So the solution the CPU employs is to hold the cache for those translations, which is called TLB, Translation Look Aside Buffer, or more specifically in this case, an instruction TLB, iTLB. The iTLB is really important, potentially, not potentially, in fact, more than the DTLB, than the data TLB, because if we don't have the next instruction, the out-of-order execution cannot hide the latency because we don't know what else we are supposed to do. Huge pages attack this directly by using a page of 2 megabytes instead of a page of 4 kilobytes. The iTLB miss rate can drop dramatically because the iTLB can cover a much bigger code base. Now, in the past, huge pages were not really used for code very often, and this could be explained by poor support of the hardware. Hardware did not have too many entries dedicated for huge pages. But this was a decade ago. This is not the situation anymore, and still, most of the executables you use these days do not use huge pages for the code. And we wanted to look at this problem to see why it is so and how we can do it magically today without changing the operating system, without changing the loader, how we can get huge pages with existing executables without relinking them. So let's talk about why it is so hard, why we don't have huge pages today. Well, 3 layers must agree in order for us to have huge pages. And I'm talking in this talk about Linux, but this is not specific for Linux. So the first thing we need to have is a file, the executable itself, that needs to be huge page friendly, let's call it, and we'll talk about it in a second. And beside that, we have the dynamic loader that is supposed to map the executable to memory. And we have the kernel that has page cache that holds those mappings of the file. They need to map the executable, the code, using 2 megabyte page. But even if the executable is mapped with 2 megabyte pages, even if the executable is huge page friendly, this does not happen in practice for reasons that the loader does not have a good facilities to convey to the operating system that it wants 2 megabyte pages for the code. And the operating system itself, sometimes, even if it gets the right hints, it doesn't employ 2 megabyte pages. And we'll talk about the reasons for that. So let's talk about the requirements from the executable. What do we need from an executable in order for it to be mapped using huge pages? The first thing that we need is what we call offset alignment. The offset where the code sits within 2 megabyte chunk must be the same in 3 places. In the file, in the physical memory, because the page cache lays each 2 megabytes in such a way. And at the virtual address, it also needs to have the same offset within the 2 megabytes, within the huge page, because that's what the hardware imposes. So if we have any disagreement on this offset in the file and the virtual address that we need to set the huge page, a huge page will not be formed. The second thing that we need to have is segment separation. This is probably more intuitive for you. This is a hardware requirement. Each page must have a very specific protection, which means that we cannot have in the same 2 megabyte region both read-only and read-execute pieces together. Now, the first requirement of offset alignment that I mentioned is, in most cases, not all, easy to obtain by just editing the executable alignment requirements. This is something that you can do with obj copy. But getting a segment separation is much harder. And why is it so hard? You may say executables are relocatable, so we can maybe move the code segment out of where it is and put it in a different place on a huge page. And to understand the problem, let's have a look at how executables are being laid out, as we can see here an example for an executable. So the ELF, the executable in this figure, has a header, and then it is composed for multiple segments. Usually the first one is metadata segment that has all kind of information like the dynamic symbols, and followed by several more segments, the code segment that come usually right after, the read-only segment after that, and so on. Now, while we can relocate, while executables are usually position independent, and we can relocate them, we cannot relocate separate segments. And the reason for that is that we have cross-segment pointers. So if we have this pointer and we decide to put the segment elsewhere, the execution will not succeed. We will have a broken executable. Now, there are tools that do that, like tools like Bolt, LLVM Bolt, if you heard about that. However, those tools are usually doing all kind of disassembly based on all various heuristics, and as a result, they might fail. In our experiments, only glibc, which is a very common library, LLVM Bolt failed. Obviously, we can do relinking, but doing relinking requires us to have access to the source code or the objects that are generated, and this is much more complicated for many deployments. If we look on existing solutions that are being used in real life, we see two kind of categories. We have copy and remap solutions and file-backed solutions. Copy and remap, which are actual solutions that are being used in real life, like libhugetlbfs and Intel's IODLR tool, do the following. They copy the code into fresh aligned anonymous memory huge page, and then they remap this region on top of the executable that they had before. By doing so, they sidestep all the problems that the page cache has, all kind of limitations that the page cache has, but they also lose the semantics of a file, because now this memory is anonymous. As a result, we don't have any more cross-process memory sharing, and we cannot reclaim memory without swapping it out, because now it's anonymous. Profilers and debuggers do not work anymore, at least not out of the box, because we don't have symbols, because we don't know that this is actually coming from a file. When we tried libhugetlbfs, we also found all kinds of bugs in it, so clearly it's not really used a lot. Intel's IODLR also, unfortunately, was recently discontinued with all kinds of Intel changes. On the other side, we have solutions which are file-backed. The most prominent solution is read-only THP, read-only transparent huge pages. This is a feature that you can compile, you can build your kernel, and it will allow the operating system, by special casing the case of executable code, to more easily form huge pages for code. Let's say that in so many words. It will do it lazily. So first you will get 4 kilobyte pages for the code, and then it will promote it to 2 megabytes, but it does not, like all the other solutions that we have here, it does not handle the segment separation requirement. So you cannot still map a page that is half, if you have a page that is half code and half data, this cannot be mapped into memory. So we wanted a solution that can be deployed today. Does not require relinking as shown here, and we have something like that. So what basically we are doing? So the insight that we have is that although we cannot move segments without having all kind of relinking, we can shift memory, we can shift part of the executable. And if we shift the right part, we can do so without knowing anything about the executable other than standard ELF layout, standard executable layout. Afterwards, we have the problem that in order to have the executable mapped into memory correctly, we need to preload it into memory in such a way that accesses afterwards will get 2 megabyte formed pages. We'll show later how we do it. When the memory is being loaded into the page cache using huge pages, when the stock loader, we are not changing the dynamic loader, later try to map the page into the executable, it will get huge pages. So the first thing that I need to explain is how do we do this magic, in a sense, of getting huge page. We can see here the original layout of glibc and how we are changing it. And the secret is that while we cannot move arbitrary segments, the code segment that is usually the second segment coming after the metadata can be shifted with all the other segments downwards. And the reason is that the metadata segment, which is the dynamic symbols and the relocation information, has a very well-defined structure. So finding cross pointers from the metadata is possible. And there are no pointers coming into the metadata from the other segments. By shifting all of those segments downwards, adding padding of trap instructions, of course, to prevent any rope gadget injection usage, we can shift all the code downwards and have a huge page that is purely code. The second problem that we have is that sometimes, because there are all kind of, the page cache has a policy of bringing stuff as 2 megabyte pages that is suitable for data and not for code, then many times we will not get huge page even if we set the executable in the right way. So to do so, we need to convince the page cache to give us 2 megabyte page to prefetch 2 megabyte segments and to map those as huge page later on. Therefore, we have a dispatcher running before the executable itself, prefetching sequential 2 megabyte segments using reads. It then maps those segments into its memory and checks that it actually got huge pages using procfs information. Sometimes it wouldn't get huge pages because of all kinds of operating systems shenanigans. In that case, it will use fadvice, it will use services in order to evict the pages that it got into the memory because it got 4 kilobyte pages. And right now, Linux does not know in a regular file system to take those 4 pages and convert them into 2 megabyte pages afterwards. So we want to evict them in order to bring them back as 2 megabytes. I'm not regarding read-only THP. This is a hack that is soon to be obsolete in the operating system. Finally, we have the story of DL open. We need to handle cases in which executables are being loaded later on, and we do it using a hook that is called LD audit, similar to LD preload that was discussed before. So let's talk about evaluation. We ran many benchmarks. We ran we ran 6 benchmarks, 2 databases, 2 web servers, and 2 compilers. We ran them on both x86 and ARM CPUs to see the behavior. Because of the shortage of the time, I will try to be a bit brief. Looking at Node.js, we ran a web server on Node.js. On the left side, on the left pane, we can see the performance. The higher, the better. And we can see that we compare 5 setups. We have the baseline Linux. We have 2 copy and remap configurations that use anonymous memory for the file instead of the page cache. And we have the 2 configurations that we compare against, the read-only THP, this emerging and soon-to-be obsolete Linux feature, and our solution. On the right pane, we can see how many TLB misses we have. We have it in misses per kilo instructions. We have the iTLB, which is the level 1 TLB, and the STLB, which is the second level TLB. When we compare the libhugetlbfs and IODLR to baseline, we see that libhugetlbfs does not provide any benefit in this workload. And that the reason for that is that this workload is dominated by libraries. And libhugetlbfs does not promote libraries to use huge pages. IODLR provides relatively good performance benefit of almost 9%. However, as I said before, this approach of copy on remap has a lot of implications on the uses of this feature, of the executable. No profiling and no sharing of memory for processes. When we look at the read-only THP, we see that performance is not that great, and there is only 4% performance improvement, and we have a very high variance, and partially we attribute it to the fact that promotion with our RO-THP, there is promotion of 4 kilobyte pages into 2 megabyte, but it happens asynchronously, it happens lazily later during the runtime of the workload. Finally, our solution provides a speed up of over 11%. And it also reduces the iTLB misses to practically, to virtually zero. With the Apache web server, we can see that that all the solutions other than ours do not provide any meaningful performance improvement. And the reason for that is that most of the libraries almost all the libraries that Apache web server uses are very small. And because of that, there is no benefit of, there is no potential to get any performance improvement. There is no potential for forming 2 megabyte pages without any meaningful shifting of the code to allow segment separation. Our solution, as shown, provides 5.2 performance improvements. And unlike other workloads, this is pretty much the only workload in which we don't have a virtual zero iTLB misses. One point that is worth mentioning is the question of whether every binary should get huge pages. And obviously, if we do that, because of the shifting that we need to do, we might waste a lot of memory if we do it for each library. Apache can have over 200 libraries being loaded. So we decided that we will try to do it only for executables for objects that are bigger than 1 megabyte. And skipping the small libraries show that it's not only beneficial from memory point of view, it also can even improve performance. We can see in the ARM case, the Apache server even providing performance degradation if we try to promote all the libraries to use 2 megabyte pages. And the reason for that, according to our understanding, is that we got all kind of thrashing on the branch predictor. It was not related to the TLB at least, because we didn't see any degradation in the iTLB and STLB MPKI in the misses per kilo instructions. To summarize, to conclude, we saw the code huge pages blocked in 3 layers, and we saw that we can actually deliver today a solution that provides you huge pages for your executables without changing the operating system, without changing the loader, and without access to the source code. Now, solutions are coming. There are solutions that come to your to Linux, but we were promised that before, and now we know that it's possible at least to do it today. Thank you, and I'm happy to take your questions.
I think they're very interesting work. So you mentioned in the beginning that you pad the code to make it 4 megabyte aligned. But what is it possible that the end of the code going to overlap with some data, read-only data or read-write data, and then you make this 4 megabytes of memory in one page, and the code should be read-only and executable, and the read and write data is kind of messed up. Is this possible?
So there are limitations that, because of the time I didn't mention. We are relying on the common patterns that we saw for executables. And we saw all kinds of patterns. And what we saw in all of them is that the code usually comes first.
Right.
And because of that, we can just shift the code forward. So I don't know if I answered your question, because to be fair, I'm not sure that I fully understood it. But if we shift the code forward and we didn't have the data before, then nothing breaks after.
But what if the data and the code share 4 megabyte of huge page? 2 megabyte of huge page. Because you have to apply the permission for the code, and then you're going to make the data as read-only. Is this possible, or?
We are not. I'm sorry. Let's take it offline. I'm sorry. I'm not sure that I fully understood. I'm sorry for that.
Oh, I had actually a very similar question. So if you don't mind, but maybe I can make it more concrete. If you go to the left image there.
To the left image.
The leftmost, right? So, just where you were, right? So if you take that code, you can't just simply slide it down a few bytes, because then you hit the read-only data, right? So you're talking about moving it down a substantial amount into a new page.
Read-only data is not backed by 2 megabyte pages. It's backed by 4 kilobyte pages. So I can just shift it down.
Okay. So you, right. Okay. So you.
There are no 2 megabyte regions in the executables today.
Right.
In most executables. So I'm not breaking a 2 megabyte just to provide 2 megabyte for the code. But even if I did, it would have been beneficial, because code is the part of the executables that benefits most from
right, but the virtual address for the code will not clash with the virtual address for the read-only
No, I'm
data.
going to shift everything down, because I kept the relative offsets the same. Everything shifts down. Okay? I shifted everything down. There is no collapse. There is no collision.
Right, but you've very carefully moved the last, and I think this answers the last question. At the bottom there, you've taken very careful. You've been very carefully moving the code so that the read-only and the read-write are spilling onto different 4K pages.
The read-only and read-write were aligned to 4 kilobyte pages before, and I didn't break it. I didn't change it.
Yeah.
I hope it answered the question.
Yeah, I think. Other questions? That was super interesting. Thank you.
Thank you.